I guess that means I could accomplish anything, huh, Mr. Miyagi?
Hey,
No sweat.
at first you accomplish paint defense. Eh?
Next, we consider yet another standard problem that can be formulated as a linear program, a mixing problem. So assume that we need to complete a painting job that requires 50 gallons of brown paint and 50 gallons of gray paint. Alright, so the particular shades of brown and gray that we need to use are described in this table right here. Essentially, any color can be obtained by mixing of what we call the primary colors, red, yellow, and blue, and depending on the percentage of each, you'll get a different shade of a color we are looking for. For example, for the required shade of brown, we need to have 40% of red, 30% of yellow, and 30% of blue. Similarly, for the required shade of gray, we need 30% of red, 30% of yellow, and 40% of blue. Now, these are the primary colors, but then mixing two of the three primary colors in equal proportions will give us what is called the secondary colors. The secondary colors are orange, green, and purple, and the orange is obtained by mixing red and yellow, green is obtained by mixing yellow and blue, and purple is obtained by mixing red and blue. We can obtain the required shades of gray and brown by mixing the secondary colors along with the primary colors. Okay, so and the availability of each paint that we have is given here. So we have 20 gallons each of red, yellow, and blue paint, and 10 gallons each of orange, green, and purple. So essentially 20 gallons for each of the primary colors, and then 10 gallons for each of the secondary colors. Now, if we run out of paint, and for sure we are going to run out of paint because we require 50 gallons of brown and 50 gallons of gray, and this gives us 100 gallons of paint total that we need. But the availability, we have 20 gallons each of primary colors, which is 60 gallons total, and then 10 gallons each of secondary colors, which is 30 gallons total. So overall we have 90 gallons of paint, and we need 100 gallons, right? So we'll be lacking at least 10 gallons, perhaps more, so it depends on whether we'll be able to use all of the available paints in order to obtain the right shades of brown and gray. So we know for sure that there will be some deficit to cover, and this deficit will be at least 10 gallons. And in order to cover this deficit, we can purchase any of the primary color paints for $20 per gallon. All right, and our goal is to minimize the amount of new paint that we need to purchase in order to complete the job. So essentially, we need to use the existing resources as efficiently as possible, and hopefully we'll only need to purchase 10 gallons of new paint in addition to what we already have. There is no way we'll need to purchase less than that, all right? So, but our objective is to essentially minimize the spendings that we'll need to encounter in order to complete the job that we have. So let's summarize all the data that we have regarding this problem. So we have red, yellow, and blue primary color paints, and then we have orange, green, and purple are the secondary colors. So let's specify the availability of each paint that we have. We have 20 gallons of red, yellow, and blue available, and we have 10 gallons of orange, green, and purple. Okay. The requirement is to have at least 50 gallons of brown and at least 50 gallons of gray. and we need to obtain this by doing the right mixing from the primary and the secondary colors that we have. So what else information do we have here? So we can purchase the primary color paints for $20 per gallon. We cannot purchase the secondary colors. So what we need to do in order to formulate the model? We need to come up with the decision variables. For this, we need to clearly understand what type of process do we deal with here. So what exactly do we decide on, and what are the implications on our objective? First, our objective depends only on the amount of red, yellow, and blue paint that we are going to purchase. So obviously we'll have to have decision variables for the amounts of red, yellow, and blue paints that we'll purchase. But in addition to that, the objective, the amount that we'll need to purchase, it is directly influenced by the way we are using the existing paints in order to obtain the right mixes. So there is some technological process involved here that we need to follow. And this process consists in mixing 6 available paints and obtaining the 2 required paints. Okay, so we have essentially 6 types of resources that we are mixing in order to obtain the 2 products. In a way, this is a typical situation. So in most models that we considered so far, we essentially try to use certain resources in the most efficient way in order to obtain certain products that we need to deliver. In this case, the resources that we use are red, yellow, blue, orange, green, and purple paints, all right? And the products that we need to deliver would be the brown and the gray mixes that we need for the painting job. Our decision on how we use the available resources to obtain the required products comes down to deciding on how much of each of the paints we are going to use for each of the mixes. Okay, so if we denote by I the index that we'll use for the available paints, and this I will belong to 1, 2, to 6. Okay, so let's number all the paints that we have by 1 through 6. So 1 will be red, 2 will be yellow, 3 blue, then 4 is orange, 5 is green, and 6 is purple. And these 6 paints are used to obtain the 2 mixes. The first one is going to be the brown mix, and the second one is going to be the gray mix. And we'll use index J for the mixes. J is going to be either 1 or 2. And the decision of how much of each of the available paints we are going to use for each of the mixes can be described by a variable xij, which will be the gallons of paint I used in mix J. And this will be for all I between 1 and 6, and J in 1, 2. Now, in addition to these decision variables that describe the technological process, we also need to specify the decision variables that will describe how much of each of the primary paints we are going to purchase. And these are the decision variables that really define the objective. All right, so let's denote by xi the gallons of the paint I purchased, where I is between 1 and 3. Alright, we can only purchase the primary colors, red, yellow, and blue, and the indices describing these colors are exactly 1, 2, and 3. Alright, so now we can easily write the objective function using these decision variables xi's. Z is given by 20 times x1 plus x2 plus x3. And this is the objective that we want to minimize. So this is our objective. Okay. So for the constraints, first of all, we need to make sure that there are at least 50 gallons of brown and there are 50 gallons of gray mix at least. All right. What's the total amount of brown mix that we produce? It's gonna be the summation of xij's for I between 1 and 6 and for j equal to 1, right? So because j equal to 1 corresponds to the brown color, so we have x11 plus x21 plus x31 plus x41 plus x51 plus x61 is the total amount of the brown mix that we produce, and it has to be greater than or equal to 50 gallons. Alright, so similarly for the gray mix, we will have the summation of x12, x22, x32, x42, 52, and 62, and this also has to be greater than or equal to 50. We can write this more compactly by saying that the summation for I between 1 and 6 of xij's is greater than or equal to 50 for j in 1, 2. So both of these constraints could be just written in a compact way by this expression right here. So this here is just an equivalent representation of these two constraints. So these constraints take care of the demand. They ensure that we satisfy the demand of 50 gallons for each brown and gray mixes. Now we need to take care of the supply. So we need to make sure that the way we use the supply or our resources is such that we don't exceed what we have and what we purchase. All right. So let's look at what's the total amount of red, yellow, blue, as well as orange, green, and purple paints that we are using for our mixes. Let's look at the red first. We use x11 gallons of red paint for the brown mix, and we use x12 gallons of the red paint for the gray mix. So the total amount of red paint that we use is x11 plus x12, and the total amount of red that we have available is 20 gallons that we have to start with, and then we purchase x1 gallons of red paint in addition to that. When we sum up 20 and x1, this gives us the total supply of red paint that we can use for brown and gray mix, and this constraint ensures that that supply is not exceeded. Next, we can write the same type of constraints for yellow and blue mixes, so let's write them down explicitly. So we'll have x21 plus x22 is less than or equal to 20 plus x2, and then for the blue paint we'll have x31 plus x32 is less than or equal to 20 plus x3. So these are the constraints for the primary colors, and then for the secondary colors we cannot purchase them, so the constraints will be a little simpler. For orange, green, and purple we'll have the following constraints. For orange, x41 plus x42 is less than or equal to 10. Then for green, x51 plus x52 is less than or equal to 10. And for purple, we'll have x61 plus x62 is less than or equal to 10. Again, we could have written all these 6 constraints in a much more compact fashion. So for primary colors, we have xi1 plus xi2 is less than or equal to 20 plus xi. This is for I between 1 and 3. And then for the secondary colors, we have xi1 plus xi2 is less than or equal to 10. This is for I between 4 and 6. These constraints are just a more compact representation of all these 6 constraints right here. Alright, so now we have taken care of supply and demand, and the last set of constraints that we need to specify would be for the technological process to ensure that the proportions of red, yellow, and blue in the brown and gray mixes are correct. So for that, we'll write several similar constraints. Essentially, we will have 6 constraints, one for each of the entries in this table right here. Okay, so let's specify this constraint for one of the entries, and then the rest can be derived in a similar fashion. For example, let's look at, say, this entry in the table, 30%, which tells us that the gray mix must have exactly 30% of the red primary color. Now, the red primary color comes from X12, but also red comes from orange and purple. All right, X42 and X62 will also be involved. So there will be 3 variables that contribute to the red paint in the gray mix. And these 3 variables will be, again, X12, X42, and X62. However, we have to keep in mind that orange and purple are only 50% red, so their contribution towards the red color in the gray mix will be only half of the total amount that they contribute towards the mix. Okay, so with this in mind, now we can write down the mixing constraint for red color in the gray mix. So we have X12 is the red that comes from the red paint, and then 0.5 X42 is the red that comes from the orange paint, and 0.5 times X62 is the red that comes from the purple paint. And now all of this needs to be divided by the total amount of the gray mix in order to determine the proportion of red in the gray mix. And the total amount of the gray mix is something that we already determined before when we wrote down this constraint right here for the demand. Okay, so it's given by the summation of all xi2s for I between 1 and 6. Let's write down the amount of gray mix explicitly. So we'll have x12 plus x22 plus x32, x42, x52, and x62. And this ratio has to be equal to exactly 0.3 because the percentage of red in the gray mix is supposed to be 30. So this ratio is 0.3. Alright, so now we can easily convert it into a linear constraint by just multiplying both sides by the denominator and simplifying the resulting expression. So we can see that this will be equivalent to 0.7 x12 plus 0.2 times x42 plus 0.2 times x62 and then minus 0.3 x22 minus 0.3 x32 and minus 0.3 x52. This is equal to 0. Alright, so we have written the mixing constraint for this entry in the table, and the remaining 5 mixing constraints for the remaining entries in the table can be written similarly. We are not going to go over the details. I will just go directly to the summary of the model, but in the process we will also review all the other details of the model that we have discussed so far. Let's briefly go over the model. Again, we already discussed the details for most of it, but again, let's review what we have done already and summarize the model. So we introduced Xij variables that represented the gallons of paint of color I used to obtain the jth mix for I between 1 and 6 and for j between 1 and 2. Then we introduced the variable xi for the first 3 paints. That was the gallons of this paint to purchase. We can only purchase the primary colors, remember. Then our objective was to minimize the summation of 20 times xi's for I between 1 and 3. Next, we specified the constraint ensuring that we have at least 50 gallons of gray mix and at least 50 gallons of brown mix. These are what we call the demand constraints. And then we specified what we call the supply constraints that ensure that the paints that we use in the mix, we actually do have them either from the supplies that we previously had or from the purchases that we had that are given by X1, X2, and X3. And finally, for mixing constraints, we looked at the proportion of each of the primary colors in each of the mixes, and we needed to ensure that those proportions are exactly as described in the table. This slide does this for the proportion of red color in brown mix, and according to our table it's supposed to be 40%, so we need to make sure that the amount of red that comes from the primary red as well as from the secondary colors containing red, which are orange and purple, constitute exactly 40% of the overall amount of the brown mix. So the primary red in the brown mix is given by X11, then the amount of red that comes from orange in the brown mix is given by half of X41, and the amount of red that comes from the purple is given by half of X61. So this is the total amount of red in brown mix that comes from all the paints that we are mixing, and the overall amount of the brown mix that we produce is given by the denominator here, and this ratio is supposed to be 0.4 according to the table. Again, when we simplify it, we obtain the following linear constraint. Alright, so this is very similar to the situation that we discussed for the amount of red in the gray mix, and this situation is again described on this slide in detail. I'm not going to go over the details once again since we already discussed this. So continuing with the remaining entries in the table, we obtain the remaining mixing constraints, and as a result, the final LP model that we get after we put everything together is given on this slide right here. Okay, so we can see that the objective is to minimize the cost of purchasing the additional primary color paints, and then the first 6 constraints are the mixing constraints. Again, each of these constraints corresponds to an entry in the table specifying the percentage of all the primary colors in the brown and gray mix. Then these are what we call the demand constraints, and these are what we call the supply constraints. And finally, we have the non-negativity of all the variables involved.